Good afternoon. My name is Geisler, and today I will be presenting the research that I have been working on with Dr. Price in the Department of Economics, Finance, and Legal Studies, as well as Dr. Shah in the Department of Mechanical Engineering. And my project is on the regional variation in the performance and longevity of lithium-ion batteries for electric vehicle use and federal electric vehicle investment distortion. So a quick overview of what I'll be talking about today. I'm going to go over the background on electric vehicles and lithium-ion batteries, move on to the more relevant literature to my research, go over the design of my research project and what I'm currently working on, and finish off with the future plans for my project. So electric vehicles, or EVs, are becoming an integral part of society today. We see them everywhere. They are marketed as greener alternatives to gasoline-powered vehicles and are said to reduce the production of greenhouse gas emissions. This industry is growing so fast that it is predicted that they will share 24% of the U.S. light vehicle fleet by the year 2030. Electric vehicles are powered by lithium-ion battery packs, which are composed of several lithium-ion batteries. These are rechargeable batteries designed with a negatively charged graphite anode and a positively charged cathode, the material of which depends on the battery type. Common types in electric vehicles include the lithium cobalt oxide and the lithium nickel manganese cobalt oxide batteries. And energy is generated when the lithium ions move from the anode to the cathode and vice versa when the battery is being charged. And the relevant issue here with lithium-ion batteries is that over time they do degrade, and they do this in two ways. The first being cycling capacity loss, and that is the loss of capacity as a solid electrolyte interface forms on the anode and cathodes, as well as lithium plating. And the second way is calendar capacity loss, and as opposed to cycling capacity loss, this is when the battery is being used, calendar capacity loss occurs when the battery is in its storage period, and this is due to self-discharge and other reactions. And the rate at which this battery capacity is lost can actually be accelerated by a multitude of factors, such as temperature, state of charge level, cycle number, and time, to name a few. Electric vehicles are currently receiving large amounts of federal funding from the U.S. government. Examples of recent legislation that involve federal funding for electric vehicles include bipartisan infrastructure law, the Inflation Reduction Act, and the Section 30D tax credit. And these include federal grants, loans, and subsidies for all three components of the EV industry, including the production of electric vehicles, the purchase of electric vehicles, and the investment in the infrastructure of electric vehicles, such as building charging stations. Now, because of the relevance of the electric vehicle industry, there is a lot of literature on the topic. However, two main papers really stood out to me and helped direct the direction of my research project and identify a gap in the body of knowledge that I hope to fill with my project. The first being, are there environmental benefits from driving electric vehicles, the importance of local factors? And here Holland and his colleagues measure the hourly emissions of 5 main pollutants from 1,486 power plants that would result from charging a 2014 model year electric vehicle for some assumed fixed driving behavior in different counties in the United States. And charging an electric vehicle in different locations actually required different amounts of energy and produced different amounts of emissions due to the fact that the energy needed to charge the electric vehicle is drawn from one of 3 main interconnections, the Eastern, Western, and Texas interconnections, that are composed of different power grids and power plants. And the authors then determined the local and exported damages from these emissions, such as pollution or air quality, and then they computed the cost of these emissions using the EPA social cost of emissions, which essentially is a dollar value assigned to the effect that emissions have on humans. And they compared this against a homogeneous federal EV purchase subsidy. And what they found was, in terms of environmental benefits, a purchase subsidy would be most effective in a state like California that has a much cleaner power grid, and actually the least effective in a state like North Dakota, which has a much less clean power grid. And we can see on the graph here on the right that the Midwest and Northeast regions had a lot more environmental damages associated with charging and driving electric vehicle than per se the Western regions. And the second paper takes a little bit more of a bottom-up approach in terms of measuring the energy use and emissions associated with driving an electric vehicle. In their paper, Predictive Modeling of Battery Degradation and Greenhouse Gas Emissions from U.S. State-Level Electric Vehicle Operation, Yang and his colleagues created a model of a lithium manganese oxide graphite battery pack and tested them under monthly hourly ambient temperature, as well as average driving conditions for each U.S. state. They tested the cycling capacity loss under an electrochemical model and the calendar capacity loss under a battery degradation model. And their first main finding was that the amount of energy and associated greenhouse gas emissions for driving an electric vehicle 1 kilometer was not constant, but actually increased as the battery degraded by 11.5 to 16.2%. And their second main finding is that battery life actually varied significantly regionally, the lowest average being 5.2 years in Florida and the greatest average being 13.3 years in Alaska. So the graph here demonstrates the results. We can see the US states on the horizontal axis and greenhouse gas emissions on the vertical axis. And by the variety shown in the data, we can see that due to temperature and driving conditions, that the emissions associated with driving an electric vehicle vary greatly over the lifespan of the battery pack. With my research, I aim to create an even more comprehensive representation of these innate regional differences and inequalities in the environmental benefits of driving electric vehicles to best inform current federal public policy. I'm going to compare the relative costs of emissions by driving an electric vehicle all throughout the United States, like that first paper did, but I'm going to take a bottom-up approach in terms of measuring the emissions and energy use as the battery degrades over time, like the second paper did. I'm going to focus solely on temperature, and I'm going to add in a new component, life cycle analysis. And a life cycle analysis would not only consider the aspects such as energy use and emissions over the lifespan of the battery pack, but it would also include the production and transportation emissions, as well as energy use of an electric vehicle, each time you would have to replace that electric vehicle when the battery pack reaches its degradation limit. The goal of my research is to answer the following question: how does the variation in electric vehicle energy usage associated with lithium-ion battery performance under climatic conditions lead to inefficient patterns of investment under current federal EV programs? And so the first step to answer this question, I will be creating an EV battery pack model. So I'm going to choose a relevant lithium-ion battery type to current EV models, as well as what is available to research. I'm going to test battery cells under different ambient temperatures, as well as charging patterns. I'm going to develop a cycling and calendar capacity loss model under varying temperatures and combine those to create a total degradation function that measures percent capacity loss per kilowatt hours used. Next, I'm going to determine the locations in which I'm going to test these models, and these are going to be based on the locations of NOAA weather stations from which I'm going to collect monthly hourly temperature data over several years and then use predictive modeling for the future ambient temperature data. For the future plans and overall objectives of my research, I'm going to measure the tailpipe emissions, or emissions associated with driving an electric vehicle over as that lithium-ion battery inside is degrading over a long-term fixed time frame. And within that same time frame, I am next going to conduct a life cycle analysis and factor in the emissions associated with producing and transporting the electric vehicle and its components each time you would have to replace the electric vehicle due to that battery aging. And then finally, I'm going to combine the tailpipe and life cycle emissions, calculate the monetary value of them using the current EPA social cost of emissions, and compare them to current federal EV investment to craft an argument for the heterogeneity of federal EV investment. Here are my references for my research. I thank you for your time, and I'm happy to answer any questions.
I think on 14 or 13, you talked about predictive modeling. Can you talk a little bit more about what predictive modeling kind of strategies or techniques you plan to use?
So the predictive modeling aspect of determining the regional locations is going to be part of the learning process, and that's going to be one of my goals for the next semester. It is something that I'm going to work with my project manager as well as his team to learn how to do and to better understand how we get data for the following years and being able to predict how electric vehicles will look and how their effects on emissions will look in the future using current and historical temperature data.
What is the purpose of testing the lithium-ion batteries under various temperatures in the lab if you're using a model to measure the battery degradation and energy consumption?
Yes, so with the model, we want to make sure that it is properly calibrated for the battery types that we are using. And so a lot of the data we are going to be collecting will be from public data sources, but through lab testing, we can test different charge patterns and different charge limits so that we can best calibrate our data. And then we're going to use the scenario that I'm going to be fixing within my research project, say an 80-20 charge limit, and I'm going to validate that my current model is using that data.
Could you talk a bit about how emissions are associated with the electricity required to charge an electric vehicle and how they compare to a gas vehicle?
Yes, so gasoline vehicles release their emissions at the tailpipe. whereas electric vehicles do not have tailpipes, so their quote-unquote tailpipe emissions are actually the emissions produced by the power plants from which the energy used to charge an electric vehicle is produced. And so electric vehicles consume energy when they are being charged, but they also consume energy in the fact that as that energy is being transported from the power plant to the electric vehicle, that also requires additional electricity. And so the goal of my research paper is not so much to compare gasoline vehicles to electric vehicles, but to emphasize the fact that regardless of which one is more environmentally sustainable, the US government is currently investing in electric vehicles. And so I'm arguing that the current investment should match the relative differences in the sustainability benefits. However, it is worth noting that the Holland paper that I did look at found that electric vehicles were more sustainable in those states like California with the clean power grid, but then actually gasoline power vehicles were more sustainable in those Midwest and Northeast regions where the power grid wasn't as clean.
So, you know, the electric vehicle industry is very rapidly growing and innovating. So, how will your research be able to keep up with that changing industry and the other developments throughout the project?
Because this industry is growing so rapidly, it is why I'm able to perform research in such a heavily researched industry, because the technology within these electric vehicles is constantly changing. The efficiency of these lithium-ion batteries is changing, as well as global temperatures over time. And so the importance of updating research, as well as taking in new perspectives, such as my life cycle analysis perspective, as well as combining in that federal policy perspective, I'm able to create a more comprehensive approach that I can continue to adapt upon and improve in the future as temperature data changes and as technology adapts.